a little bit about why. So float on top. A little bit about why we are. Sorry, this is not all supposed to be visible to y'all. This is just an example, so I didn't, you don't really need to have the notes printed out. All the notes are is just this. So you just have a sheet of paper and you can write it on. So let's talk about why we're using Laplace transforms at all for just a moment. Let's step back. I told you, I sort of gave away one of the punchlines, is that the S that we've talked about a lot, the S that shows up in our transfer function, is equivalent to the Laplace transform S. Okay, and actually the derivation for the transfer function with the Laplace transform is almost identical to the one that you guys have seen. I didn't focus on the fact that it was the Laplace transform S before, but now we're going to say, okay, since it is the Laplace transform S, that means that when we are writing our transfer function, and we're writing things in terms of the ratio of the output complex amplitude to the input complex amplitude, what we're really doing is we're relating Laplace transforms of these y and u, the output and the input. Okay, so that fact is like I think an important fact, and I don't really know a good way to sort of I could have made like a lecture that was just stating that fact. Probably should have, I guess, to make sure it was very obvious that this is an important fact. It's an important fact, and we're just going to apply this fact in this problem, okay? And use it. We can use it to talk about transfer functions then, and to find solutions, because you guys have all learned how to find Laplace transforms and inverse Laplace transforms. So let's just do it for this problem. So we want to use the Laplace transform to do this. So the first step is, let's find the transfer function. I mean, technically you don't need to find the transfer function, but I think it's worth going through and seeing that. So let's do that. So no. The driver's not working. I got my laptop back, but the driver's not loaded, I just now realized. Okay, we're going to have to just talk through it, because I can't write it. So you guys will have to just write along. Unfortunately, my tablet driver is not loaded, so I can't write. And I don't have good enough control on my mouse to write with the mouse. So the first step is to take the Laplace transform of both sides. Like, remember we did with the Fourier transform, right? But the Laplace transform is very related to the Fourier transform, and we do that. So the Laplace transform also distributes in a summative fashion. So we can take the Laplace transform of this term, Laplace transform of this term, etc. And it's a linear operator in the same way that the Fourier transform is. And we can pull out constants like the 3 and all that. So the Laplace transform of y we write as being y, capital Y of s. Okay? So this Laplace transform of y that shows up from this becomes just y of s here. Okay? And the Laplace transform of u, so you can pull the 2 out, the Laplace transform of u is just u of s. Now I wrote at the top of your page, if you have this printed off, the Laplace transform of any function of time with lowercase symbol, our convention is to write it as an uppercase of the same letter as a function of s. So this is just shorthand for, so f of s is shorthand for Laplace transform of f of t, just as u of s is shorthand for the Laplace transform of u of t. Okay? So it's all very similar to the Fourier transform. And also, that's the convention you guys learned when you learned Laplace transforms too, right? That's pretty standard, I think, even for math folks, not just engineering folks. So, look familiar? Yeah, sound familiar. So these ones are easy. So Laplace transform of y, I just write as y of s. Laplace transform of 2u, okay, 2 times the Laplace transform of u. Easy enough. The first one, the first term is the term that takes the most work. And that is, it's 3 times the Laplace transform of the derivative of y with respect to time. Now, let's see if we can find on the website what the in the resources, if we have a Laplace transform table, let's see. I haven't uploaded a specific one that's separate, but it does show up in these general system dynamics notes. So here we go, Laplace transforms. I'll upload a separate document too, so you don't have to go looking for it in here. But Laplace transform properties. In this table, the one that we need is the Laplace transform of f prime, which is the derivative of f with respect to whatever variable it varies in. And we see that it's just s times the Laplace transform of f minus the initial condition. Okay. I think that's familiar to you guys. I think that should be familiar from your differential equations course. You're welcome to use the table that you used in your differential equations course too. They're all equivalent. Some of them have properties that others don't. So let's go ahead and use that and say, okay, s times the Laplace transform of y minus y of 0, the initial condition. And a very common mistake is to not realize that the 3 is multiplied by that whole thing. But that is the case. So don't put the 3 in front of this guy and forget to put it in front of this one. That happens like half the time almost. Like, it's so common. Okay. Just get caught up in the Laplace transform and you forget about the 3. Okay, so this can be solved for y of s, right? So it's algebraic now, so we can solve it for y of s. You can, this initial condition term does not have a y of s in it, right? So you have to add it to both sides. So we get 3y0 on the right-hand side that shows up. And we divide both sides by whatever you get when you factor out y of s from the 2 remaining terms. And divide both sides by that, which is 3s plus 1. And we get this for y of s. Now, technically, so you guys probably, at this point, would have just said, okay, now we need to take the inverse Laplace transform to solve for y of t, right? We're going to slow down for just a moment and figure out what the transfer function is. We have it, it comes along for free. And what the transfer function is the term that relates y to u, okay? This initial condition business is not part of the transfer function. That's a really important thing to notice. The transfer function is only going to tell you about the steady state response. It doesn't tell you anything about the initial condition contribution, okay? So that's when we derive the transfer function the other way. That was the assumption we made there too. The Laplace transform, though, is a little bit more powerful than just that. You can take into account the initial condition by keeping around that initial condition and taking the inverse Laplace transform, and that's what we will do here. So what we do is we don't really have to factor. We just separate these two terms and we say, okay, there's a term that multiplies u, and then there's a term that multiplies the initial condition, right? We just separated out this factor here, and we said, okay, there's 2u of s divided by 3s plus 1. That's one term, and then there's 3y of 0 divided by 3s plus 1. That's the other term. And the transfer function is what you would get if you just ignored this initial condition completely, this term, and you looked at the relationship between y and u. So if you divided both sides by u here, then this would be y over u equals, and then whatever is in this term that multiplied u, that's what the transfer function is. So 2 over 3s plus 1. We knew how to identify it from, even from the original equation. We could have maybe been confident enough to say, oh, the transfer function here is just 2, because there's this factor 2 here, divided by 3 times, there's a time derivative, s, plus, and then the coefficient of y is just 1, so 3s plus 1. So we knew what the transfer function was, but I just wanted to show you where it shows up when you use the Laplace transform method, okay? Yeah?
Even when you're like y of 0 equals something other than 0, you're still going to drop that because the y of 0 is...
So you drop it only to find the transfer function.
Yeah, steady state. So even if, like, I know in this case, so y of 0 equals 0, but if y of 0 was like 10, you'd still lose it because that's your initial response, not your steady state.
Yeah, so you're right. So in this case, y of 0 does equal 0 for part A. Yeah. But in problems where there's not a 0 initial condition, you can still do this just to say, oh, well, what's the transfer function? We'll say set y of 0 equal to 0 just to find the transfer function. And then we can go back to our original problem with the initial condition in it. In general, y of s is equal to this compound expression where you've got the transfer function in there. So this is h, we define it as h. So this is h, this is u. So y is equal to hu, and then this initial condition term. So add the initial condition term. And what we're going to do is to take the first input and the initial condition. So we're going to do part A, which is the unit ramp. Okay. So I said, okay, if the unit ramp is the input and the initial condition is 0, what is the solution? So if you plug in y of 0 equals 0, this term on the right, which came from this term up here, right? That goes away. That's all 0. And you're left with this. Now, but when you want to solve for y of s, you need to know what u of s is, right? U of s is the Laplace transform of the input, right?
Where did the s squared come from?
This one?
Yeah.
So this is what I'm talking us through it.
Oh,
So u of s is going to be 1 over s squared, but how do we know that? So we said that the input is the unit ramp function, just t, okay? That's the unit ramp function. And if we look in our Laplace transform table, so these are the properties in this part, and then you come down here and you get a bunch of functions. Oh, look, if these are the Laplace transform pairs. If your time function is just t, which is a ramp function, then your Laplace transform is 1 over s squared. I mean, you could plug it into the definition of the Laplace transform too, the integral, and integrate, and you would get 1 over s squared. So that's what we plug in as our u of s. So the u of s in this expression just becomes 1 over s squared. That make sense? So in this expression here, this is the transfer function. This tells us what y of s is for any u of s, for any input. But we have to know for a specific input what that Laplace transform is, what u of s is. And we happen to have a ramp function as the input. That was we say, okay, if the unit ramp function is our input, so u of t equals t, we go to our Laplace transform table and we say, oh, that means that our input so our u of s is equal to 1 over s squared. All right? So we're running out of time, so I do have to keep moving. So that is the expression. So this is for the specific input and initial condition. This is our y of s. Okay? Just combine these two fractions together. So now all we need to do is take the inverse Laplace transform. So to go from y of s to y of t, take the inverse Laplace transform. And taking the inverse, so what I'm doing here is I'm rearranging this Laplace transform of y to be in a form that I can look up in the table. Okay? So let's look in the table and see what we've got. Okay? We've got some things that are, so what we have is like a ta s plus 1 in the denominator, and then we've also got that multiplied by an s squared, right, in the denominator. So if we look in here and we look around, do we see anything that looks about right? Well, there's this, right? Right, it doesn't have that s squared in front of it, and you know, 20 is close, but this is s squared. I don't know if you guys shows up very well, but this s is squared. So that doesn't quite work either, because our s inside the parentheses is not squared. So what is our move? So we don't have one, I don't think, that is this specifically. So you could separate them out. There is a let's see. I think there's another option here. Well, I mean, the way that I'm seeing it now, so there might be another property we could use that's like I think there is a pre-fabbed one for us, but I can't see it at the moment. Whoops. I don't see it at the moment. So let's take the one that said it was e of t, and then we'll use the property that 1 over s is an integration. Okay, so it's bigger. So we can use this one, and then we're going to use the 1 over s squared to recognize that you have to integrate that twice. Okay, which I think at the top of this table, yeah, so you could use this integration of a function property here. If it's 1 over s in the Laplace domain, you have to integrate in time. And so that's what we're going to do. We're going to do it twice because we have two 1 over s's. We have to integrate twice. There's another property I think that could get us there without having to do the integration. I can't remember it though. But we can always integrate. So what we do is we say, oh, this is e to the, now the table had it written as s plus a, and so I had to write it as s plus a here, and I had to factor out of 3 to make that happen. So that's where the 2/3 comes from now. The 2 is already there, the 3 comes out of this denominator, and we get 1 over s squared plus, or s squared times s plus 1/3. So we have e to the minus t over 3, and we also have the integration that happens twice, and that's where we get to here. I'll try to find, there's a property that I think that gets us all the way to this without having to do the integration.
Let's say 2 over 3 times 1 over 3 squared, or is it an S?
This is 2 over 3.
The next one down.
Below it.
Yeah,
Where
down
you
right
have your
there.
y of t equals.
Yeah, what's
there.
this?
So this is 1 over 1/3 squared.
And then what's the next?
Is that an 8 or a 3?
That's a 3. Yeah, it's hard to see. 1/3 t minus 1. And then you just expand it out, and this is what you have. Yeah, so that's essentially, I wanted to kind of go through it quickly and give you guys like a refresher on it. You guys used a table too, right? When you guys learned how to do this?
Integration stuff, it was just table in it.
Just the table straight up?
Everything was pretty much kept in the form that was in the table.
Yeah. And there is so I did not go over partial fraction expansion. You guys remember that?
Oh, God.
Yeah.
Was it like the, oh man, I know, yeah.
And because this is the thing. If it comes in a form that isn't in the table, you can do a partial fraction expansion and write it as a bunch of sums of things that do show up in the table.
So you're saying expansion, is that also called decomposition?
No.
I always heard it called partial fraction expansion, but partial fraction decomposition could be true too. Partial fractions is the thing. So
Where you separate it out and then you have your A, B, C.
yeah,
And then you
yeah,
solve for your A, B, and C.
yeah. So you do that so that you can get it written in a form that shows up in the table. So that is also possible. You might have to do that. I'm going to stop the lecture now.